Okay.
Enhanced Fujita scale. And so Fujita. Now we have enhanced scale. There it's more precise. Just not very glorious.
Anybody know how to move this? Alright, the brightness temperature of the radiation is the black body temperature that would yield the actual brightness at frequency omega, and that implies the following.
This K will be small K.
Once again, we gotta do this.
And what is that one?
So the brightness temperature ends up being defined as this quantity here. That's K. Okay.
And that one should be there. That
which one? This?
Yeah. Before the omega square. Maybe 1 by.
Based on here, I'd say it shouldn't be there.
Or maybe it's just a 1.
Yeah, it's multiplied.
She wanted to multiply by 1. It's okay. No harm by that.
Okay. So in equilibrium, the effective brightness temperature is just the energy of the emitting electrons divided by this numerical factor. And in any case, when we write it this way, when we write E as a function of omega, the ratio of omega to omega cyclotron, there's a fudge factor here. Which apparently was kept. Now, the inverse Compton catastrophe sets in when the energy density in photons exceeds the energy density in magnetic field, which means that the n plus first generation of Comptonized photons is going to have more energy than the previous one by induction. And now in practice, it doesn't go on forever because you run into the photons keep getting harder, and eventually they stop being Thomson scattered, and they become Klein-Nishina scattered, and the cross section is lower. But still, if you have a weak magnetic field, like in interstellar space or intergalactic space, and you have so much bulk, the cloud is big enough that the amount of synchrotron radiation that gets built up is more than the original magnetic field energy, then you basically have ripe conditions for a inverse Compton catastrophe, where you keep generating more and more energy by inverse Comptonization of existing photons. From the photon's point of view, its expected gain in energy is greater than its probability of escaping. So the just total energy in photons just keeps building up until it's enough to slow down the electrons and to cool the electrons. And then you probably get a Comptonized, well, if it's a high optical depth, you would just get a Comptonized photon spectrum, and it would be like gray body. It would have the shape of a black body, but with less photons. Yeah.
I didn't understand why the second generation has higher energy than the first generation.
Well, the first generation had more than the magnetic field, right?
Okay.
By definition. And the ratio of the second to the first, assuming you're still in the Thomson scattering limit, is the same as ratio of the first to the magnetic field. Each one, the expected gain of each generation photon is greater than one. It's like rabbits. With each generation, it's more than the previous generation.
But why? I still don't understand why the second generation has more.
Why did the first generation have more than the magnetic field?
They depend on the magnetic field, no? And the energy.
That's right. It does. It does. But I already said, by hypothesis, I said it.
Yeah, if you say this,
I say inverse compensation sets in when this condition holds.
Yeah, this, okay.
But if this condition holds, then this condition also holds.
This one I don't understand. Why the second one?
Because the amount in any generation is proportional to the number of electrons times gamma squared times the energy density in the previous generation. And if that ratio is greater than 1, it's greater than 1. If it's greater than 1, it's greater than 1.
Why skip?
If it was greater than 1 for this condition to hold, so it's going to be greater than 1, and therefore this condition holds.
Where did they get the...
Why doesn't it enhance the escape probability of photons?
Because I'm assuming that the Thomson, we're still in the Thomson scattering limit, and the Thomson scattering cross-section is independent of energy.
Yes.
So, by Comptonizing the photons, the Comptonized photons have the same probability of being Comptonized again as the original photons had. And as I said, eventually that's no longer true. Eventually they'll get to high enough energy where they're in the Klein-Nishina limit and the cross-section goes down. So then this argument no longer holds. But if the original photons were, if the original synchrotron photons were in the radio,
What is this age here? Why do you wait before you move on? What is the proportionality?
I'm just trying to expand the damn screen.
NE.
You take
So
the
U n plus 1 proportional to n e gamma square. What is bar? And u h, what is h?
Should be NE n plus 1.
I don't know, I think we did it the day you got married or something.
What?
You have to go back to the lecture that you missed.
It was in...
in video exam.
Okay. I thought that you didn't talk about it.
No, now we're missing a whole page here.
What is on the screen?
Average of those.
So U n is energy density previous generation and U n plus energy density.
It's supposed to be n. Okay.
So 3, page 3.
You know what? put a copy of the old course notes here because you're missing more pages.
It's went down probably.
No, this just went from page 2 to page 4. We're missing page 3. Here.
Yes.
Okay. So let's figure out what the energy density of photons is. It's dominated by photons, again with the highest frequency that's still in radiative equilibrium with the electrons. At lower frequencies, not only is the omega squared phase space factor lower, but the brightness temperature is also lower, as you'll find out doing the homework. So let's say this is the maximum Lorentz factor of the electrons, gamma max, that are in radiative equilibrium with the photons, with the synchrotron photons. We can then say that the energy density is equal to 8 pi kT per cubic wavelength. That's roughly the energy density in photons. And cubic wavelength is just C over omega cubed times pi squared. Because there was an 8 pi up here. Maybe there should still be an 8. I'm not sure. No, because it was pi over 2 or 2 pi or something. So I substitute for kT with gamma max mv squared over alpha plus 2. That was the effective brightness temperature. And this is the frequency of the emission. It's gamma squared times the cyclotron frequency. All cubed because it's per cubic wavelength. And therefore the condition that the magnetic energy be greater than the photon energy is simply the v squared over 8 pi be greater than this quantity, which was just this quantity.
You're talking about energy density, right?
Yep. Now, this condition can be rewritten as follows. Since there's a gamma to the 7th that shows up, gamma max has to be less than this quantity to the 1/7 power, which when you work it out is a little bit more than 100. It's about a little bit more than 100, and this is B1 in Gauss. Or, B divided by 1 Gauss. And in interstellar space, let's say you have a field of a microgauss, this is less than the factor of 10. And if on the surface of a neutron star where B could be 10 to the 12th, this is still only a factor of less than 100. So the point is that to a very good approximation, 10 to the 2.2, 2.3, it's about a factor of 100 to 200 times the electron rest energy is the maximum energy at which electrons can be in equilibrium with synchrotron radiation and not have an inverse Compton catastrophe. So below the emission of electrons that have this Lorentz factor, 10 to the 2.2, you can have synchrotron self-absorption. If you want to have synchrotron self-absorption of radiation that's even beyond that, that's okay, but then you'll have an inverse Compton catastrophe, and you probably won't see anything like this. You'll see all kinds of all the energy going into gamma rays. So here's the point: if you see radio emission from a distant source, you don't know what the size is, but you know what the brightness temperature is, because the brightness temperature cannot be greater than gamma max. Here I rewrote B to the 1/7 in terms of the frequency of emission and gamma, and you can just rewrite the condition this is the condition that you have no inverse Compton catastrophe, and you say gamma has to be less than a certain number times B, but since you're observing it at frequency omega, and you know that gamma squared is equal to omega divided by this, because well, it's EB over MC, and if I write that in terms of B is 10 to the B is just B1 Gauss, and if I just write EB over MC for 1 Gauss, I get this number. So I can replace this B to the 1/7 with an omega, and I get the gamma max is less than this. Now, if I'm observing at radio frequencies that are not much different from 10 to the 11th, maybe it would be a gigahertz would be 6 times 10 to the 9th. Maybe this could be a factor of 100, and 100 to the 1/5 power is a small factor. Anyway, you know from B to the 1/7 that it's a very modest factor. And that sets an upper limit on gamma max, and therefore it sets an upper limit on the brightness temperature of what? An upper limit on the brightness temperature of KT brightness has to be less than gamma max m sub b c squared, and let's remember the alpha plus 2, so we know what we're talking about. Well, the electron rest mass, if you translate that to temperature, KT equals the electron rest mass, that's about 10 to the 10th, a little bit less than 10 to the 10th degrees. And if I multiply that by gamma max, which is less than 10 to the 2.2 b to the 1/7, so maybe it gets up to 10 to the 12th degrees. But the point is, I can never have a brightness temperature that's higher than 10 to the 12th degrees without getting an inverse Compton catastrophe. Because it would simply mean that the photon energy density is larger than the magnetic field energy density, and that's the point of no return. And the inverse Compton process becomes like a sorcerer's apprentice, where you just can't stop it and it takes over. And again, what probably happens is that you get lots of pairs, and they do a lot of comptonization, and they finally recombine, and you just get a fireball that's about between 10 and 100 keV in energy.
That's what
Of the
everybody's
photon.
talking about, the flare from Mother.
Well, that's what I think they're talking about. They don't always admit it, but yeah, that's what they're talking about. Sometimes the early models of gamma ray burst like to suggest that it's optically thin synchrotron radiation, and that's what the gamma rays were, first generation synchrotron radiation. But they never did explain why it always comes out to be of order, 100 keV to an MeV, or sometimes it's a few MeV. But and they said, well, it was selection effects, because you have spacecraft that are looking in that spectral range, so that's what they find. And eventually they found X-ray flashes at lower energies. So I have a running dispute with the rest of the community, but there's but in recent years, people have started believing that it's not an optically thin synchrotron, that it's really a photosphere from an optically thick surface. And now all they have to do is explain why the temperature is, 100 keV to give you a 300 keV peak, and they'll be all set. But that's the topic of ongoing research and arguments. I just sent off an email to somebody about that a couple of days ago, and so far he's not answering. But this 10 to the 12 brightness temperature was an issue decades ago, long before anybody knew that gamma ray bursts were cosmological, uh, uh, now certainly for gamma ray bursts, this is a big problem because well, I'll get to that in a minute. Let's go in historical order. The first problem arose when they saw galactic nuclei See, before I couldn't get this to go on, now I can't get it to go off. See, if I just click long enough, it goes off, but it's like doing a rain dance. Oh, I'm still missing another page here.
Yeah, from 3 then 4.
Yeah, but
What is it?
3 then 4. Maybe
You're not supposed to use this.
that one.
wait a minute. Yeah. Okay. That might explain what some of the problems were.
Maybe it goes down to it some portion.
No,
After 3 then there is 4.
anyway, this should be the general features of the radio spectrum. That you have a, well, I'll let you do the homework, but there should have been a graph here. I know what happens. You cut and pasted 3 and 4. One on top of the one below the other. So
maybe just, insert some space, then that will.
Yeah.
Well, I'm gonna have to do it right here. Now what happened?
Go down.
That did not work out.
Nothing. You can just press some space there. Yeah.
And then move it up.
Yeah, you can move it.
How do I move it up?
Just press the below part and press it. I mean, just click it diagonally. This part, maybe diagonally. Right, this here. So diagonally, if you. Yeah, it's a 3 is ended there.
You put in page 3, and this is page 4. I want to get it to go down. I just want to slide this down.
Maybe 4 you can slide. Maybe.
No.
Maybe you can slide the
On
4.
PowerPoint, there are arrows.
Yeah, here you don't have.
Why don't you go to PDF and see if it's there?
What?
Why don't you go to PDF and
No,
see
how do I just slide this down?
Yeah, from that portion you can.
It just disappeared. I'm trying to grab it diagonally here. It won't grab. Here we go. No, I think what happens when you cut and pasted, you miss the graph.
No. I may take the select all. The whole portion has been selected. I didn't paste it manually. I copy it manually. I just do it select all.
So how do I grab this and get it to go down?
Yeah. So there is the third page is finished there.
No, it's not there.
No, it's not here. It's just not here.
There
There's
PDF
materials.
and see if fuel efficiency there.
If what? No, I don't have time. I'm just going to draw. I'm just going to draw the general features. Basically have a self-absorption region and then a power law spectrum optically thin and then a break where it's cooled. That's all I wanted to do. So this is self-absorption, this is optically thin, and this is the cooling frequency. Alright, so now let's go back to here.
What is the last one? Cooling.
Where the electron's already cooled. Alright, where did page 4 go?
You have to go move it to right. Yeah, you have to move this to right. Yeah.
So in the first part goes as omega to the 5/2, and in the middle is omega minus
alpha
plus
1
1
over 2. And here it steepens by a factor of 1.
So is it a plot of the say the spectrum
Okay. So now here was the problem historically. Sometimes they didn't know how far away a radio source was. Distant radio loud quasar, say. But they knew how much flux they were collecting. And let's say they knew the redshift of the host galaxy. So they didn't know how far away it was, but they didn't know how big it was. But they knew, since they knew how far away it was, and they knew how much flux they were collecting, they didn't know the brightness temperature, but if they guessed this, they knew the brightness temperature is a function of size. Now, suppose they saw it vary. The nuclei of galaxies, of radio loud galaxies, put out, puffs of radio, and they vary on the human time scale, even on time scale of an observation. So they would see radio sources getting brighter and dimmer on, I don't know, scales of days maybe. It depends. Some are fast, some are slow. But certainly they changed their morphology totally on the time scale of less than a year. And for some BLAC objects, the time scale of variation can be hours. And in the gamma ray emission in the X-ray and gamma ray regime, they see flux variation as small as 10 minutes. They're starting to believe it. The last I heard, they hadn't gone away after 10 years, 15 years. They're still seeing things on time scales, variations, time scale of minutes. But let's go back to the radio. Even in the radio, whatever the time scale was, they set a limit of CT, or T is the characteristic variation time scale. They set a limit of CT on the size because The assumption is you can't have, in time 1 second, you can't have a region that's bigger than 1 light second turn on all at once. It would be like the conductor waving his wand and the orchestra all starts exactly at the same time before the light from the wand can propagate to the back rows of the orchestra. It's an assumption that it doesn't happen, and therefore they set a minimum velocity time scale of variability in the source limits, and here I'll put a question mark because it's a hypothesis, size to be less than c tau. Now, if you put in the source, the maximum source diameter that's consistent with that, delta theta, it has to be less than c tau over the distance to the object. And let's say you know the distance to the object because you see the redshift of the host galaxy. So you assume what this is, and then if you know the angular diameter and the flux, you know what the brightness temperature is. Because the P of omega, the omega has to be equal to P of black body omega, d omega, times delta omega over 4 pi, right? If you're sitting inside a black body and you're seeing from all directions, you're seeing 4 pi at a given brightness temperature. So if you're seeing it from some fraction of the sky, it's whatever fraction of the sky it was contributes to the flux. This would be the all sky, what's called the all sky flux. You know, you sum the flux coming from all directions. Now, this gives you the
Why can you use this black body?
what?
Why can you say those is black body? Spectrum?
I didn't say it. I said that if it's going to be self-absorbed, the maximum brightness temperature, the maximum brightness temperature always occurs here, because for constant brightness temperature, this would continue to go up as omega squared. Here it went up as omega to the 5/2, but from here on it goes down. So the maximum brightness temperature can only be where where there's still marginally synchrotron self-absorption, and that means you're at the black body limit. Now, it could be less, but let's give it the in fact, let's put it in. It has to be less than the black body. So this sets a lower bound on the brightness temperature, right? Because it sets a lower bound. What did I call the brightness temperature of the photons? T photon. Alright, sets a lower bound on the brightness temperature of the photons. Okay, now that's all well and good. The problem is that the lower bound occasionally would be greater than 10 to the 12th degrees. Okay. No. Now I'm missing the next.
Oh, it's on the right. It's on the right.
Yeah,
It's
it is on the right.
Go down.
Down?
Yeah.
Is there any way to get it back?
Yeah.
Wait, that?
Oh, this. Yeah, anyway, the solution was to assume that it's coming at you at almost the velocity of light. And then, the best way to say it is that because of the blue shift, the brightness temperature that you see is much bigger than the brightness temperature inside the source. What we set a limit on for inverse conflict astrophy was all in the frame of the electrons, of the electron gas. Well, that should be obvious, right? The arguments about energy density, photons being greater than that of the field. So that set a limit on the brightness temperature in the frame of the plasma. But now if you assume that in addition to the relativistic electrons, they're moving relativistically in the frame of the electron gas, but if you assume in addition that the whole thing is moving in bulk at and here we should change. It's become customary now to write bulk Lorentz factor with a capital gamma. So we should make this capital gamma. And this is probably a small c. So let me say that the conclusion that it was accepted historically is that P of omega d omega and let's say this is the maximum black body of omega delta over 4 pi. Now here's a big K for Kelvin.
Supposed to be lower than 10
no, but I mean the T photon that you needed to account for the observed. In fact, let's call it apparent brightness temperature. So the conclusion was that the gamma is equal to or greater than T photon apparent over 10 to the 12th degrees. This, of course, is all based on approximations. So if you saw a brightness temperature of 10 to the 13th degrees, you attributed the factor of 10 difference to a blue shift, factor of 10. And for gamma ray burst, you had the same problem, and it was even worse. There you had to assume a factor of, well, doing it just with brightness temperature, they had to assume a factor of there was one gamma ray burst in particular where they did it using the brightness temperature of optical synchrotron radiation. They assumed that the optical radiation they saw associated with the they saw prompt optical emission. That was what happened. This was GRB GRB 990123. It showed, it was a very bright and hard gamma ray burst. It showed prompt optical emission. There's also been one since then, whose name I can't remember, that was even brighter. And I think I'll assign it as a homework question. Yeah, that could be homework for next week. observe let's call it an isotropic equivalent energy output of it could be 10 to the 50th ergs for in the case of a gamma ray burst, but it's in, let's say that we know it's in synchrotron emission. And it comes within delta t, which could be as low as 30 seconds, or even 1 second. Find lower limit on gamma, and there's one more thing. I have to say it's at frequency nu. All you need is E iso nu and delta t, I think, and that's enough to find a minimum lower limit on gamma. And you should be able to do it based on this lecture. But the idea is to get a general formula. For GRB, it came out to be about 50 when they saw prompt optical emission. And that was really a lower limit. It could easily be 100 or 1,000. They derived other limits there was another one that Rahul worked on where it was at least 1,000, but that was based on gamma ray opacity, which was a different argument. The point is, whenever you find something that doesn't quite seem consistent, you can often solve it. You can often solve the problem with high Lorentz factors. Now, there was the reason that became popular in the 70s and 80s was that they had another problem. They were actually able to map radio clouds
it's a right down.
Yeah, I know. Had another problem, which was apparent expansion velocities that were greater than c. In other words, they would see a source doing this, and we had a lecture on it. Yuri last week showed a picture in his lecture, and then a year later they see it's like this, and a year later they see it's like this, and they just plot this as a function of time, and it comes out to be 10c. And he discussed how it's solved. If its source is coming at you at a gamma of 10, it looks like it's, even though the angle is one, even though the real velocity projected transverse line side is 10th c, it's multiplied by gamma squared because of the 1 minus beta factor in the departure time and arrival time. It's what we discussed already for synchrotron, for the individual electron for synchrotron emission. The reason the frequency goes up is because the time is compressed, and it's the same thing here for the cloud of incoherent synchrotron emission. The whole thing is moving at you. So also that implied that gamma was at least 10. So that solved both the problem of high rapid variability and apparent superluminal motion, faster than light motion. And then with gamma ray bursts, it's clear that as soon as you do the first homework, it's clear that you need gamma much greater than 1. It solves all kinds of problems. Okay. Now, the next thing that I have in my notes is the derivation of Fermi's golden rule.
Was this projected velocity in our frame? See, 10 times speed of light.
It was on the sky.
Yeah, in our frame. Even in our frame, nothing should move faster than light, right?
In our frame, yeah.
Even if you project any velocity.
I'm not sure what you're asking.
In our frame, nothing should move faster than light.
Not really.
Yeah, not really.
But
that gamma.
In anyone's frame, nothing should move faster.
But the projection on the sky can appear to move faster than light because time is sped up by gamma squared.
That's apparent.
The apparent, yeah. Now here,
Right.
the next thing in the course notes is the derivation of Fermi's golden rule for quantum mechanics, and I'm not sure why. Well, since I was talking about photons scattering after inverse Compton scattering. By the way, all these k's are wave vectors, and they should be small, but I'm not going to worry about that now. So, if you want to calculate something like scattering of relativistic particles and particle decay, that's actually an emission process, like when pions decay. It's any decay process, you find the decay rate using Fermi's golden rule. But I think that I'm just going to skip this because there's so much in the course. So the next topic is let's see. Chapter 1. Just decided not to move.
Right.
Great. Just what I needed. Okay, it doesn't move. Alright, let's try this. Oh look, did it decide to move? Great. Occasionally it decides to move. Do you remember where we're up to? That looks like B1.
Chapter 2 has been done.
So C1. Yeah, I think I want to start with Maxwell's equations now. I guess I want to how do I get this full string? Never mind, I just want to copy it. How do I copy it? No.
You have to click this C1, then the PDF will come.
Here's I did.
No,
this is the PDF.
No, this is the preview of that. You just double click on that. Yeah. So.
Okay. Oh, so that's why it wasn't working. Alright, so now I want to take snapshot.
Or right click. Right click, and then you can also call the select all. Then if you want.
What?
Yeah, select all. First which has been selected.
So it's one page.
Yeah. Then.
Now I want to go back to. I want to go back to what? I was in what?
OneNote.
So first of all, I want to minimize this.
Then you have to copy this one. Select, after select, you have to copy selected graph.
Yeah, and then.
Then in the OneNote, you have to go to OneNote.
Where was OneNote? Oh, it was down here.
Yeah. A new page or something. No, paste. The paste option is there, and below the paste option there is an image. Yeah. Click inside that.
Easy boy. You know, if in PowerPoint you just press it, there's just an arrow somewhere. Alright, that'll have to do. So anyway, Maxwell's equations, there they are. Differentiate number 2, equation 2 by time, take the curl of equation 1, and you get this. And you probably have all seen this at some point or other in some course. Assume e to the I kx minus omega dependence, and you get this. Now, in a vacuum, k dot e is equal to 0. Why? Because it's just Poisson's equation, which is not either of these.
Divergence of E is equal.
These are only 2 of 4 Maxwell's equations.
Right.
But there's also div b equals 0 and div e equals 4 pi rho. So in a vacuum, k dot e is just div
E equal to
e, which is equal to 0. Therefore, this is equal to 0, and also j is equal to 0.
Right.
So that's what you have in the vacuum. Now, if you have a medium, you can still have waves where k dot e is equal to 0, but j is not equal to 0. So then you have to calculate j in terms of e. If you calculate j in terms of e, you will get an equation that contains just e, and it'll be a dispersion equation that you solve again just like this. You just get this extra term here, which means that it'll be different from before. So here's how you calculate j. You just say it's the density times the velocity times the charge. And what's the velocity? Well, you solve the equations of motion, which is that to get dx I dt, you just say that m times x sub I double dot is equal to e, and you get that x is equal to e over minus omega squared m sub e, and x dot is equal to e over I omega. Eventually I'll write a magnetic field. First, let's do it without the magnetic field. But the point is, that's the simplest. This is in the simplest case, where it's just a bunch of particles. But here, I'm being general. I'm just writing the j is equal to dp dt, and I write p as some tensor times the electric field. And this is always right to linear order, because even if there's a magnetic field, even if there's a background magnetic field, if there's no electric field, nothing's going to happen. But since there's a wave, there is an electric field, and the response of the particles is linear to that electric field. And finally, I define epsilon this way. This is actually a definition. Epsilon is 1 plus, this is an omega. In other words, epsilon is equal to 1 plus 4 pi I just a second. This here is 4 pi omega squared chi e. So this here is I have a 4 pi, I have an I, and I have a chi. What? And chi, by the way, can be a function of omega.
But the third equation means that it's equal 0 because of the second equation? It doesn't make sense.
Because if you put this term over here, you just get 0. And this is this term.
Just a second. Just a second. Let's start over. Epsilon is 1 plus 4 pi chi. Where chi is defined. Didn't I just define something? Alright, let's say this is a definition, and this defines chi. Which means chi is equal to it's just a tensor that connects connects J and E. So chi is equal to
You can write J is equal to omega chi E.
I don't have to write anything. This is just fine. We just use epsilon, and know that, and remember that epsilon is 1 plus 4 pi chi. All right. So for k dot 0, we just get the k squared is equal to epsilon omega squared over c squared, whatever epsilon may happen to be, and calculating epsilon is what plasma physics is all about. It can have an imaginary part, and the wave can grow. So we'll get to that in a minute. But the point is that I can have k dot E equals 0 even when there's no vacuum. But I can also, and why is that? It's because I can just pick a mode where E is perpendicular to K. And therefore it just happens to be 0. But I can also pick a mode where K is parallel to E. And then the solution epsilon equals 0.
Because k dot E is
K dot E is KE, and therefore the left-hand side happens to be 0, and therefore epsilon must equal 0. So this is the solution.
But why is k parallel to E? We had previously...
because I can pick a K. See, here's the thing. Any solution to equations you have to consider. If it solves the equations, it means it's allowable. Doesn't mean it's obligatory, it just means it's allowed in nature. And if you can excite it, it does the rest. It simply obeys Maxwell's equations. So the real question is, how do you excite this mode? And the answer is, well, it can be arranged. Alright. Now,
you can right click and select all. Then copy the selected part.
And now minimize this.
The note, one note.
Doesn't just stay on the Okay, now there's also a definition of D, which you've also seen in Jackson, and it's what the field would be
measured for
If-
only plasma or
If
anything?
not, it should be if not for the
Doesn't
measured
matter.
plasma, right? If not, if not for the plasma. In other words, it's what the field would be if you subtract the part that's due to the charge separation in the plasma, or the current in the plasma. And E is what the field really is. That's what you get if you measure the field there. So it's always confused me, because it seems to me that epsilon, the inverse of epsilon, is the more intuitive quantity. Because if E is equal to epsilon to the minus 1d, and by the way, epsilon is a tensor. It's a second rank tensor, and these are vectors. This D would be the applied field, and E would be the real field corrected for the plasma. And this would be like, sort of like an impedance, which tells me, if I apply D, what do I end up getting out? D is the input and E is the output. So when epsilon equals 0, it's really poles in the impedance, which means that I don't have to put anything in, but I get something out. Which means for an electrostatic mode where epsilon is equal to 0, it means that the plasma is sustaining an electric field on its own, without any help from any outside sources. So that E is 0. No, E is non-zero, but D is 0. And it's just the plasma is doing it all by itself. And therefore epsilon equals 0 represents the poles in 1 over E, and tells you the natural oscillation frequencies of the plasma. It's like applying a force to a mass on a spring. If you apply it exactly at the resonant frequency, and there's no damping, you can get an infinite amount of amplitude for a finite amount of force. You just have to wait long enough. But that happens at the natural oscillation frequency of the spring, and here too it happens at the natural oscillation frequency of the plasma. Now, this seems to just be a review of what I said. Maxwell's equations give this, and you find the eigenvalues of epsilon such that it just becomes such that this epsilon is an eigenvalue of this tensor. Now, somebody wanted magnetic fields. I guess we should have a homework where you just find the plasma frequency, which is the frequency at which epsilon equals 0. Frequency at which epsilon equals 0. the density of electrons, the charge, and the mass. And that might seem easy, but at my age nothing amazes me anymore, so I just do it so I know you know it.
Can I tell you this now and finish the homework?
What?
Can I tell you this now and finish the homework?
Yeah, please do. And then hand it in anyway, but you tell me. Go ahead, tell me.
Square 4 pi n e power 2 over kBt or over m.
You think? Okay, good. When you're sure, write it down and hand it in.
This is the answer.
And while you're at, you can derive it
Yeah,
so that you'll be sure.
It's in multiple choice.
Now, suppose there is a magnetic field, then life gets a little bit harder.
It's 4
Right, okay.
Thank you very much.
So this is a good place to stop. Did I?
It's on right here.